Here you see that we want to minimize the projection error. So in case of projection error, it will go like that. Okay, that means the shortest distance from the point to the line. So that means if I want to compare, so this is what we have in this PC. So if you want to see them simultaneously, you see that the green one is basically represent the error for linear regression. The blue one is going to.
Yes.
Okay. So this is actually what we have talked about. The same thing can happen. So in this case, if you have multiple eigenvectors to represent this plane, that is U1, U2, this we have plane over here. So what will happen? All these points will be projected on this plane. If you think like this, will be projected on this plane. And similarly, you have to compute this perpendicular distance. Okay, which I draw in red. You have to compute this perpendicular distance. This is going to be what we see in case of PCA. This is what's going to happen over here. And we know for sure that in case of PCA, since we have two projection lines in case of it is 2D space. Okay, if we talk about this 2D particular space, so let's say one, that one. So since we also want to maximize, okay, we have to maximize the variance. So if I say that among these two lines, though we have to pick both of them maybe sometimes, but if you want to choose among U1 and U2, which one will give you the maximum variance?
U1.
The green one, right? Because this is here. This one will okay, let me select okay. Let me draw like this. Green one. So this one will come over here, this one will come over there, this one there, this one. So you can see that they will be spanning throughout this whole space in case of the green one. And if I take the blue one, you see the blue one, all these points they will be projected here and here. So they will have a variance of this much. So since you have to maximize the variance, so the green one will be the one that can maximize the variance, right? Okay. Now we'll be talking about this PC algorithm for specifically for dimensional reduction. This is what we're going to focus on. Okay. But before that, we look at the steps. So in case of steps, what we do? We'll first do the subtraction of the mean, that is from the data mean. From the data, we'll subtract the mean. So basically, this is the pre-processing step. Then step number 2 and 3 is very important. We have to calculate the covariance matrix. Okay. And then from this covariance matrix, we have to find the eigenvectors and the eigenvalues. And once I have computed the eigenvectors, then we can choose which eigenvectors I want to pick. And once I have chosen the eigenvectors, okay, then basically we'll generate a new feature vector. Like this is the new feature vector that we'll be looking at. So if I go one by one, so that means if we have n number of samples, okay, all these samples, so can we compute the mean of all those samples? Yes or no? It's very easy, right? You can simply compute the average, which will give you the mean. Okay, so if you consider from each of these elements, because in case of this feature vector x, this will have a lot of elements like x1, x2, up to xn. Okay. So computing the average means basically if you have a lot of samples, let's say you have a lot of samples. Okay. So let's say this is the first sample we're talking about, and this is the nth sample we're talking about. Okay. X1, x2, up to xn. So what do you have to do? In order to compute the average, so if I want to compute the average over here, so what do you have to do? You simply have to compute the average of all the elements, first elements of all those n samples, so this will give you the average mu1. Then the second element, if you take all the average, with the average mu2, and so on, you will get all those n average for those n elements, right? Yes or no? And once we have got the average, so we have to subtract the mean. Let's say if you have this ith sample, okay, you simply subtract the mean. Okay, so this is what we need to have here, this mean subtracted samples. And there's an optional step that you can do. You can also do the scale. Like since we have said that the different feature elements will have different scale. Let's say the outside, the number of bedrooms, maybe a lot of feature elements will have different scale. So if we do this scale normalization, what will happen? All of them will become a range of, let's say, maybe 0 to 1, or maybe -1 to +1, or maybe -0.5 to +0.5. So there are a lot of ways you can do this. normalization. You can have mean max normalization. You can have z-score normalization. Okay. Is this clear? So once we have done this mean subtraction, basically what kind of effect do we have? The data becomes centered, where the mean position will be the origin, right? Yes or no? Have you understood?
Yes, sir.
For example, if I look at this particular picture, so you can see all these data that we have over here. So where will be the average, the mean position? So this is going to be the mean position, right? Yes or no?
Yes, sir.
And then if from all the sample, let's say from this sample, if I subtract the mean, what will happen? You see that here we have the origin over here before doing this mean subtraction. After doing this subtraction, you see that at the mean position we have now the origin. Yes or no? That means after doing this mean subtraction, and then if you again compute the mean of the new sample, the mean position will be exactly at that 0, 0, right? Yes or no?
Yes, sir.
Okay. So we see that if we use mean subtraction, the next step was to compute the covariance matrix, and basically by subtracting the mean, this will have no effect on the variance or invariance. Okay. For example, if we have all these data, how many samples do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means we have 10 samples. Each of these represents one particular sample. Okay. Though they have used here x, y, but we can say now this is x1 and this is x2. You can think in this way. So for all those n samples, okay, can we compute the average of all these x1? Of course, I can compute the average of x1. Can I compute the average of x2? Yes, I can compute the average of x2. And if I subtract whatever this vector we have found, this is the mean vector. Okay, if I subtract from the first one, what will happen? I will have the mean subtraction. If I subtract from the second sample, what will happen? I will have the second mean subtracted sample, and so on. And you see that if you again want to compute this mean of all this data, you'll see that this will become close to 0, 0, right? Yes or no?
Yes, yes.
Okay. Now the next step is basically to compute the covariance matrix. So, do you know about covariance? What is the difference between variance and covariance? Can someone tell me? Nobody?
So I think in variance we look at how one variable is spread across a particular range, and in the case of covariance, I think we relate that to two variables, if I'm not mistaken.
Okay. So basically, once we look at like this, let's say we have this, let's say in this case of one this space. Okay, let's say you have this data spread over. So if I compute this variance, so this is how much they are varying with respect to the center. Maybe the center might be somewhere there. With respect to the center, how much they are varying, right? This is what we compute by variance. Let's say with this random variable, let's say this is this random variable of x. What will happen? Variance of x is something like 1 by m summation of for all those m number of samples. Okay. Oh, sorry, mean of. You just compute this and you get the square, right? Yes or no? But you see that in case of covariance, we compute between two random variables, x and y, and you see that this is distribution into 1 by m, summation of from the samples from 1 to m is going to be xi minus mean of x. Then we will have, let's say, if we consider another random variable y, so it's just going to be yi minus mu of y. So that is basically, if I say covariance between x and x, this is equivalent to basically computing the variance of x, right? Yes or no? Is it clear?
Yes.
Okay. So that means instead of xi square, I can simply write xi minus mu xi. So that means if this is y, so this part simply becomes yi minus mu of y. Okay. So basically, what does covariance give you? Covariance basically gives us the relation between if one variable x is varying, then how does y vary? This is what basically this covariance will give you. For example, if I look at this particular data over here, then if I have done mean subtraction, now we can see that the data are somehow scattered something like this. Okay, so that means if the value of x1 increases, then the value of x2, is there a tendency of increasing together or decreasing, or it doesn't depend on that one? Which one do we have here?
Increases.
Exactly. That means that we have a tendency that if x1 increases, then there's a tendency that x2 is also increasing. Or if x1 is decreasing, then we see that the x2 has a tendency of also decrease. That means basically what we see from the point of correlation, this basically there is a positive correlation, and from the point of variance, you see that between these two random variables, x1 and x2, we have some positive covariance. So okay, I should have written variance. So that means you can see that between correlation and covariance, there is a kind of relationship, right? You see that in case of Pearson correlation, the Pearson correlation is going to be equal to covariance divided by sigma of x and sigma of y. Okay, so this is the relationship between correlation and covariance. So that means covariance, if you normalize by the variance of x and variance of y, okay, that's the standard deviation law. So what do we have actually here? The correlation will be within the range of +1 to -1. This is what we're talking about, correlation. But covariance, the values will be something like some plus value to some minus value. Is this clear? Yes or no?
Yes, sir.
That means covariance will be having some positive value. Positive means positive correlation. And negative covariance means there will be some negative correlation. Understood? So now we can see from here, that means if x varies, how will y vary? This information we can get it from the covariance. Okay, but we are talking about covariance matrix. What does it mean, actually? It's a matrix, right? Yes or no? It's a matrix. Okay, fine. Now let's say in your sample space, how many feature elements do we have? Let's say for a particular sample, say x, we have x1, x2 up to xn. For the time being, let's say for this example of this 2D space, let's say for this 2D space. So basically you have to deal with x1 and x2, right? So you see that the covariance will give you the relation between the different feature elements like this. So if we say this particular value is basically representing the covariance between x1 and x1. And this element basically represents the covariance between elements x1 and x2. And this one is going to be covariance x1, sorry, x2, x1. And the last one is going to be covariance between x2 and x2. So basically, in case of the 2D feature space, this covariance matrix will be of a size n into n, right? Yes or no? Is this clear?
Yes, sir.
So that means basically, let's say if you are working in this 3D space, let's say if your feature space was 3D, let's say if your feature space was 3D, then you have x1, x2, and x3. Then your covariance matrix will be of size of what? 3 into 3, right? Yes or no?
Yes, sir.
That means you will have the covariance between the elements 1 and 1. The next one it will be 1 and 2, and then it will be 1 and 3, right? Yes or no? Then the second row where you will have the covariance between element 2, 1, 2, 2, and then 2, 3. The last one is going to be 3, 1, then 3, 2, and then 3, 3. Now if I ask you the covariance between element 1 and 2 and the covariance between 2 and 1, are they same or they are different? Are they same or different?
This will be same.
Covariance matrix. First of all, you will see that we will have a square matrix, and also it's going to be symmetric. Understood? I don't know if you can right? Yes or no? Now, how about if I give you a figure and you tell me how will this covariance be represented? So let's say in this 2D space. First of all, this 2D space, the covariance matrix will be of size of what?
2 by
2 by 2. So now, let's say here, these diagonal elements, the first diagonal element is going to represent what?
the variance.
So in this case, you see that the variance in the x1, let's say this is x1 and this is x2. So this means these two represent the variance in the x1 direction. So whatever the value you have, so it's going to be some value, let's say some value of let's say a. In case of, let's say, if I talk about this variance in the x2 direction, so the variance is how much? So it will be varying like this much. So let's say it will have a variance of this value of b, 5. How about the off diagonal elements? What value do you expect over there?
They should be negative because
Yes,
of
negative value. Right? Since it's symmetric, so it's going to be some negative value, right? Okay, let's have another example. Let's see what you think of it. Okay, let's say something like this. I have to be a little bit careful about this one. Okay, let's say it's a nice elliptical shape over here. So now if I want to draw and write the values, tentatively I want to write the values of this covariance matrix of this data. Okay, so what we can say? The variance in the x1 direction is going to be some value a, because it is varying this much in the x1 direction. In the x2 direction, it is varying maybe this much, so it's going to be some value b. And of course, you can see that the value of a is greater than b, right? Because the variance in, let's say this is x1, this is x2. So do you think you have more variance in the x1 direction compared to x2?
Yes, sir.
Okay, fine. How about the offline elements?
I think this is 0.
Which should be 0, because you can see that there is no dependency between x1 and x2. Is this clear?
Yes.
Okay. And how about if we had something like this? Okay, if I remove everything again. How about if I had a nice concentric circle? Okay, something like that. How would this covariance matrix look like for a data distribution like that? First of all, the variance in the x direction, the variance in the y direction, they are same, right? So it's going to be something like this. And since they don't have any dependency or variation, they don't have any dependency, but here it's going to be something like that, right? Yes or no?
Yes, sir.
So that means basically now, instead of looking at the picture, if I didn't give you the picture, but if I only give the covariance matrix, can you tell me the shape of the distribution of the data? Yes or no? You can give me, right? Let's say if we have something like this, the value of b is greater than a, or let's say the value of b is less than a. How do you think the data shape will look like? How will it look like?
So it should be spread more towards the x2 direction.
Exhibition, maybe it's something like this, right?
Yes, sir.
Yes or no? And you can see that if we have some values of x, so let's say some value of a little bit like same thing, but I had let's say minus some value, let's say 3. And what will happen? That means there's something different, right? That means the same thing, maybe it will go like that, right?
Sir, I had a question. Sir, when we have b in the first element of the matrix, aren't we calculating the variance along x1 for that?
Yes. So that means this is for x1, right? 1 is the 1, 2, 1, 2. So this is the variance in each direction. In the x1 direction. And this is the variance in each direction.
Oh,
So the variance on x2 is larger than the variance in x1.
X1, yes sir.
So that is you are varying more in which direction?
In the x2 direction
X2
also.
direction. And you are varying less in which direction?
In the x1 direction.
X1 direction. So that's why the shape will become something like that.
Yes sir. Yes sir. Got it sir. Thank you.
Got it?
Yes sir.
Okay. So this is what we have over here. So already we have seen that for the previous data that we have seen over here. So you can see that the data, if you look at how this data has been distributed over, okay, you can see that the data have a relationship something like this, okay? Maybe something like that. Okay? So we can see that okay, there is some variance in the x direction, there's a variance in y direction, also there's a positive covariance between them. So that's what we can ultimately see from this covariance matrix. Okay? So you can see there's a positive value, right? What does it mean? They are positively correlated, right? And you can see the variance in the x direction and the variance in the y direction are quite close to each other, right? Yes or no? And at the end, you can see that this covariance matrix, it basically gives us the information about the shape of the different distributions, how the data are distributed in the original figure space. Is this understood?
Yes sir.
Now next, what we do, once we have computed the covariance matrix, we have got the information of the data spread. Now what we need, since we have said that because of TC, we have to have this direction of data variance. Okay, this is the direction of data variance, something like that. So we can see that that same direction can be found easily from these eigenvectors and eigenvalues from that corresponding covariance matrix sigma. So I believe you know about this singular value decomposition, right? Yes or no? In linear algebra course, you have learned about this SVD, right? Singular value decomposition, where a matrix A, let's see if there's a matrix A, it can be decomposed into three different matrices. One is U, one other is S, another is D transpose. Yes or no? So you will see that in our case, since we have got an n by n square matrix, it is symmetric and also it is square. You see that once we have computed this matrix U, that is this matrix U, we find that it's going to be an n by n matrix, and those n by n matrices you will see that each of the columns are basically they are representing one of the eigenvectors. Okay, so that means each of these are basically eigenvectors. Is it clear? Yes sir. Is this clear? So that is the example that I have shown you is in this 2D space. So if I compute the eigenvectors, how many eigenvectors will you have? How many eigenvectors will you have?
2 eigenvectors.
Exactly. Each of the eigenvectors will have how many elements in it?
2 elements.
2 elements, right? So that means once you have computed the covariance matrix, and if I draw, that means for a 2 by 2 matrix of this covariance matrix, if I compute this U matrix, I mean this is going to be capital U. This is going to be the first eigenvector U1, and then we have the second eigenvector U2. And how many elements? Let's see if I talk about this, the eigenvector. How many elements do you have? You will have U1, U2. That means you can see that the eigenvector will also lie in the same space, right? Yes or no? And interesting, you see that the first eigenvector will be pointing in this direction, and the second eigenvector will be pointing in that direction. So that means we can see that the first eigenvector is pointing in the direction where you have the maximum variance. Yes or no?
Yes, sir.
And not only that, you will see that if we look at this matrix S, the matrix X is going to be also is going to be an n by n matrix. And you see that in that matrix you will have some diagonal values, and all the off diagonal values are going to be 0. That means you have a diagonal matrix like that. Now, interesting, you see that that matrix S, that means you are considering this one. Okay, that matrix S will contain the eigenvalue, that is lambda 1, lambda 2, up to lambda n. So that means in this particular example, for this two-dimensional cases, so your S matrix will be again 2 by 2. And how many diagonal values will you have?
12.
Two values. You will see that the first eigenvector is u1 will be corresponding by lambda 1. The second eigenvector will be u2, okay, with the corresponding lambda value of lambda 2. And you will see that the value of lambda 1 will be greater than lambda 2. Because the lambda 1 is basically, it is representing, it's going to represent the variance. Okay, if I write like this, it's going to represent the variance in UR. So if I write like this, lambda I will represent the variance in UR. So in which direction you have more variance, U1 or U2 for this data?
So U1 direction.
Okay, that's why you see the lambda 1 bigger than lambda 2. So now if I consider, for example, if I consider a 50-dimensional space, let's say you have a 50-dimensional space. So if you compute this covariance matrix, that means this sigma matrix, it's going to be a matrix of 50 into 50. And from here, if I compute this eigenvectors, so how many eigenvectors will you have? 50. How many lambda values will you have? The corresponding lambda values will be also the result I will be from 1 to up to 50, right?
Yes, sir.
And you see that if you sort them, if you sort all those lambda values and if you plot them, don't you think the thing will be something like this? Right. Let's say this is lambda 1, this is lambda 2, this is lambda 3, and basically in this direction we are essentially plotting the magnitude of the lambda. That is the value of lambda. Is it clear?
So do we have to sort this manually or will it automatically be sorted?
Normally in your calculation, it will not come in a sorted order, but in the built-in functions in MATLAB or in Python, if you use the built-in function, it will sort it for you.
Okay.
So that means if I say this way, among all these eigenvectors, which eigenvector has the highest variance?
The first one.
First one. And the second largest is which one?
The second one.
Second one. And then so on, right? Now we can see from here, if you have the eigenvectors, okay, arranged in such a fashion that they have become something like this. That means you have n eigenvectors, and you can see that only the first two eigenvectors have data variance, and from the third and onwards, you can see all of them are close to 0, maybe something like this, 0, 1. What does this mean actually? So it means that basically I can simply pick the first two and I can discard the remaining eigenvectors. Can I say like that? Can I say like that?
Yes.
Why? If I give you another example over here, let's say I give you 3 points. Okay, this after mean subtraction, the points are, let's say this one, and this one. Okay, let's say this was -1, this was 0, 0, and maybe the other one was 1 and 1. So if I compute the eigenvectors, so we can see that easily the eigenvectors will point in this direction, one in this direction and one in other direction, right? Yes or no? Right?
Yes, sir.
Okay, let me pick another color. It will be easy to understand. Let me pick orange color. Okay, this is orange. Now, let's say if I pick both of the eigenvectors, that means u1 and u2, axis u1 and u2, how will your points look like?
The data will be towards the x-axis.
Exactly. Don't you think it will look like that?
Yes, sir.
So as if since you have defined a new coordinate system, don't you think that you have transformed your data from one coordinate system that was basically x1, x2 to the new coordinate system defined by u1, u2? Yes or no?
Yes, sir.
Okay, and according to the new coordinate system, the values are represented by like this. This is going to be 0, 0. This is going to be some value of a0, and this is going to be some value of minus a0. For example, let's say if I think like that. Yes or no? That means with PCA, what have we done? We have transformed data. Can I say like this? We have transformed the data. We did, right?
Yes, sir.
Now we can see before doing this transformation, the values, the data samples, were they positively correlated?
Yes, sir.
Okay, fine. After doing this transformation, okay, after you have transformed it, the same samples, you have 3 samples, both of them are basically in this 2D space. But after doing this PCA, the values, are they positively correlated or they are independent now?
There is no correlation.
There is no correlation, right? So that means with PCA, the first thing we have done is that we have transformed the data from the old space to a new space, where in the new space the data are uncorrelated. Can I say like that?
Yes, sir.
Okay, fine. But have we reduced the dimension, feature dimension?
No, sir. Still same.
Okay, why we couldn't reduce the feature dimension? Because all eigenvectors were picked, right? Yes or no?
Yes, sir.
Okay. Now, if you want to reduce the feature dimension, what do you have to do?
We can take the most prevalent vector and
Exactly. So you can just simply the top k eigenvectors.
yes.
Yes, sir. Okay, fine. In case of 2D, we have to have less than 2, right? Yes or no? So let's say in case of 2D, if I have to pick only one, because if you pick all 2, then basically you don't have any dimension. So you have to pick one in this particular example. Which one will you pick? U1 or U2?
So U1.
Okay, how about if I picked U1? Sorry, if I didn't pick U1, I picked U2, how will your data look like?
It will be skewed in a single point.
That means you're simply removing U1 from your scene. And if you remove U1 from your scene, you'll see that the first projection value, because you're projected on what? On a single axis, that is U2. All of them will project to 0, yes or no?
Yes.
So how much variance do we have after doing this position on U2?
So 0 variance.
0 variance. But if I did the other way around, it was minus A0, so 0, 0. If I picked U1, what would have happened? That means you are bringing U2 out of the scene. U2 of the scene means that the second element is out of the scene. Then 3 values are there for those 3 samples. And how much variance do we have? You have quite a significant variance over there, right? Yes or no?
Yes.
And that means basically, if you want to maximize variance among these 2, which one you will pick?
U1.
U1. So if you were in this original space was, let's say, 1000 dimensional, and then if you want to pick only one, which one you will pick? The first eigenvector, right? Because lambda 1 would have been the highest. Yes or no?
Yes, sir.
But basically, you see that in terms of information, you lose a lot of information. You might lose a lot of. Maybe you want to pick the topmost 30 of them. Understood?
So, sir, this is like another hyperparameter.
Yeah, exactly. This is another parameter that basically you have to select and then see what happens. But there is some way to define it using some threshold. We'll talk about that soon. But do you get the point?
Yes.
So instead of 1, if I want to pick the topmost k number of them, let's see if I want to say the k number of them, then your feature dimension will reduce from n to what?
Okay.
Okay. It is understood.
Yes.
So this is actually what we will do in the next step. That means if you are to pick the highest eigenvector, that means the best fit line, Because the base fit line is basically what we are calling as the principal component. And this principal component is found from where? Found from the eigenvectors. And what you have to do? You have to sort those eigenvectors in order of significance. That significant means in terms of these eigenvalues. And once I have got these eigenvalues, among those n eigenvectors, how many I will choose? I will choose the top k of them, right? Yes or no?
Yes, sir.
Now the thing is very simple. If I pick one eigenvector, if I do the projection of one eigenvector, how many coefficient values will have? You will have a single coefficient value, right? So in this way, if I project on the second eigenvector, I will have the second coefficient. So in this case, if I project on all eigenvectors, we will have how many coefficient values? But did you do dimensional reduction here? We did
Not yet.
So if I pick k of them, now you see that we have done dimensional reduction, right? Then previously the value of x was x1, x2 up to xn. After picking k of the eigenvectors and doing the projection on, you can see that we have to do this projection. So after you do this projection on k of them, your new feature vector z represent that sample x will be represented by z1, z2 up to zk. That means z is basically, it belongs to this k dimensional space. Is this understood?
Yes, sir.
So can you see that if we do PCA with all the elements, this in this case, what have we done? We have simply done this transformation, right? But with this help of transformation, what's the benefit? The correlated variables gets what? Gets uncorrelated, right? Yes or no?
Yes, sir.
And then if you want to do dimensional reduction, that's what you have to do. You have to discard the eigenvectors, right? That means you cannot take all eigenvectors. You have to take the k eigenvectors. That's when your dimension will reduce from n to k. Is this clear?
Yes, sir.
So up to this point, do you have any question? So basically, how do we do this projection? This is very simple. We simply compute the dot product between the sample. Let's say that if the sample was something like, let's say if you have picked this matrix U, which has been reduced. So you see in some cases we write U reduced. So that means the first element is U1. If you write like this, U1. Second element is U. Element means the vector element, and after you have picked UK. So how many vectors have you taken? You have taken k number of eigenvectors. And then if you have this sample x, that is x1, x2 up to xn, that means I have basically taken x transpose over here. But you can see easily from here, if I take the dot product between x and u1, what will you get?
Sir, the x projected towards u1.
That means you get z1, the first coefficient projected on u1, right? Yes or no?
Yes.
Then if you do the projection on u2, that means x dot u2, what you will get? You get z2. So in this way, if you project on all those k number of samples, you end up with up to zk. Yes or no? Right?
Yes.
Okay, fine. Now, if I want to do the other way around, what should I do actually? That means from z, that means it is something like this. Something like this. So if you want to get, so let's say this is your matrix U. So if you want to get x back from z, how should it look like?
U transpose into z.
Sorry? U inverse z, right?
Yes, sir. Yes.
Yes or no?
Yes, sir.
And the interesting thing is that since these eigenvectors, first of all, they are orthogonal to each other, right? That is, ui is perpendicular to uj. Not like this. I mean, ui is perpendicular to uj, right? Yes or no?
Yes, sir.
First of all, the eigenvectors are orthogonal to each other. And not only that, the magnitude of these vectors is equal to 1. That means this matrix is going to be an orthonormal matrix, right? Normally, in case of matrix, we say orthogonal matrix. We don't say orthonormal. It's going to be